Hi students, these notes are over 10.2, congruent chords, and 10.3. 10.2's essential question is how can I apply the relationship between congruent chords of a circle to solve problems? Here are two theorems that are converses of each other. The first says if two chords of a circle are equidistant from the center, then they are congruent. So if you look at one of these circles below, I'll show you what that means. So if you have two chords and they are equidistant from the center, which just means they're the same distance from the center. And when we're talking about distance from one thing to the other, we're talking about the shortest distance that's implied. The shortest distance from a center to a chord is always going to make a right angle with that chord. So what this is saying, if these two short distances are the same, then that means the chords themselves are congruent. And if the chords are congruent and they have just been bisected by this perpendicular part of the radius, then that means these four halves are also congruent. So that's how you would mark that on your picture. The converse of that states that if two chords of a circle are congruent, then they are equidistant from the center. So very similar. So if you've got two chords, they are congruent. That means if I draw a line from them to the center of the circle, those distances will be congruent as well. And again, those distances will make a right angle with the chords, and those distances, those tiny distances from the center to the chords will also bisect those chords and make those four halves congruent as well. Okay, so here's an example. Let's try to apply these theorems to this picture. It tells us that AB is congruent to CD. AB and CD are these chords. Because the chords are congruent, we know that these distances from the chords to the center are also congruent. We're also given expressions for those, OP and OQ. So all we really need to do is set those equal to each other to find the value of x, and then we can plug in the value of x into the expression for OP. So let's do just that. So 12x minus 5 equals 4x plus 19. To get our x's together, we'll move the 4x to the left by subtracting it from both sides. 8x minus 5 equals 19. Add 5 to both sides to get our constants on the other side. 8x equals 24. Divide both sides by 8. So x equals 3. To find the length of OP, we will plug in 3 into the x of the expression that equals OP, 12x minus 5. Just plug it in here. 12 times 3 minus 5. 12 times 3 is 36. 36 minus 5 is 31. There's the length of OP. Easy peasy. That was 10.2. So let's look at 10.3. 10.3 is over arcs of a circle, which we haven't talked too much about. The essential question is how can I apply the relationships between congruent arcs, chords, and central angles to solve problems? So an arc are all of the points on a circle between 2 points. It's kind of like a curved line. A line are all the points between 2 points, going straight from one point to the other. But on a circle, we've got to follow the path of the circle. So for example, if I have point A and point B on this circle, the arc is this curved part between them. This is called a minor arc. There are 3 types of arcs we will look at. A minor arc. Oops, hold on. A minor arc has a measure that is between 0 and 180. And when I'm talking about measure, I'm talking about if I was to draw some radii from the center of the circle to the endpoints of the arc, the measure of that angle that it creates is called the measure of the arc. It's also called a central angle because it comes from the center of the circle. So the way that we would write an arc, it's kind of like writing a segment. Instead of a line on top, it's a curve on top. And then to represent its measure, you will just put an M in front of it, just like for the measure of an angle. So we would write it like this. The measure of arc AB has to be bigger than 0 and less than 180 degrees for it to be a minor arc. Okay, another type of arc we have is called a semicircle, which you probably are familiar with this. And a semicircle is an arc that has a measure exactly equal to 180 degrees. So the way that you would draw that, the endpoints of the arc are actually going to be the endpoints of a diameter of the circle. Here's the arc. The arc just follows the path of the circle. And if I was to connect the radii from the center to the endpoints, those two radii together are going to create the diameter, or a diameter of the circle. The measure of that angle that it creates with the two radii is exactly 180 degrees. So the last type of arc we have is called a major arc, and it is larger than 180 degrees, but it's got to be less than 360 degrees. So if I have 2 points on a circle, there are 2 ways that I can connect them. I could connect them like we did with the minor arc in the shortest path. That would create a minor arc. But if I connect them going the other way, now we've got a major arc. And the way that we denote a major arc is we have to incorporate another point from that arc. Because if I just called this arc AB, that assumes the shortest path, like in the minor arc over here. So to emphasize that I want to include the larger distance between A and B, I need to put another point, label another point on the major arc part of it. And when I name it, let me write major arc really quick. When I name it, I'm going to use 3 letters. So it would look like this. The measure of arc AXB, like that. And the extra letter needs to be between the 2 endpoints of the arc. So the measure of a major arc has to be greater than 180 degrees, because if it's equal, it's a semicircle, but it's got to be less than or equal to 360 degrees. Can't be bigger than 360 degrees. So the arc itself, the measure, if I draw the center of the circle and I connect it to its endpoints, I'm not measuring the angle of its minor arc, I'm actually measuring this angle right here. Okay, so when we're talking about an arc, there are 2 values that we can associate with an arc. Arc AB is going to be this curved part right here. Now it has both a measure, which is the measure of the central angle formed from the radii that join the center to the endpoints of the arc, and that's actually an angle measure. So for example, and I'm talking about this one right here, for example, we could say that the measure of arc AB is going to equal the measure of angle AOB. These 2 things mean the same thing. you're used to the right hand notation, but the left hand notation is new. And I need y'all to know that that's actually talking about an angle measure, degrees of an angle. The other number or value that's associated with an arc is actually the length of that curved piece. And that's actually just a portion of the circumference. So if I take off the M in front of the arc symbol, now I'm talking about that length of the curve. And that is always a portion of the circumference. Like I said, circumference is 2 pi r. That would equal the entire circumference, but since we're just talking about a part of it, the way you would find that is you would find 2 pi r, and then you would multiply that by the portion of the circle that is represented. And what you can do to find that portion, you can actually make a ratio from that central angle right there. It's measure. So the measure of the central angle over the total angle measure of the circle, which is 360. So for example, if that arc was 100 degrees, I would put 100 over 360 and multiply that by the circumference, and that would represent the portion of that circumference, that distance from A to B around the circle. And by the way, this is all, we actually skipped 9.2. If you need some more information on this, it's actually part of 9.2. You can just go back to that part of the book. Okay, so what we've got here is a circle with 2 chords, and where those chords intercept the circle, at these 2 points and at these 2 points, they are going to create some arcs in the circle. Okay, we can also sketch in some radii from the center to the end points of the chord, which are also the end points of the arcs. Dotted lines don't work so well on the iPad. And what that's going to create are some central angles here. Those central angles are the measure of those arcs. They're also measure of those central angles. So there's a thing that you guys got to know. Let me just tell you real quick. If these 2 arc lengths happen to be congruent, okay, so we've got congruent arcs, we'll say arc lengths, or it could be arc measures, the lengths or the measures, and or what we can do is we can assume then that these chords that are made from connecting the endpoints of the arcs, those chords are going to be congruent as well. So congruent chords. And then in addition to that, that means that these angle measures of the central angle, or the measure of the arcs, those are also going to be congruent. Or we can say, we can call them measure of arcs. I guess we could write it like that. Kind of looks messy. So here's the deal. If, I'm going to circle this for a second. If any one of these 3 things is true, then all 3 of these are true. So write this down. If any one of these is true, then all are true. Okay? So if you've got congruent arc lengths, that means you've got congruent chords and congruent central angles. If you've got congruent chords, then you have congruent central angles and congruent arc lengths. If you've got congruent central angles, then you also have congruent arc lengths and congruent chords. So this is super big to remember, and that'll help you when you're solving these problems. Now keep in mind also, the radii are always going to be congruent, right? So that could possibly help you when you're solving these problems. And if you think about that, the two radii with the chords are going to create some triangles. By SSS or SAS, those two triangles are also going to be congruent. So you've got a lot of congruent things here. So you also have congruent triangles. Okay, lots of congruencies. Just if two things are congruent, then all these things are congruent. And going back to the triangles, I'm talking about these, this triangle, and this triangle. Okay, so use those concepts of congruency when you're solving these problems. You can always set the congruent parts equal to each other. Remember also what you can do is you can always draw a segment from the center to the midpoint of the chords, and those are going to create right angles, which are going to create right triangles. And the two right triangles that it creates, those are also going to be congruent. So all of this is some good stuff to remember. Okay, so let's finish up with an example. It says find the length of chord, I think it's of the chord, that cuts off arc of the arc measuring 60 degrees in a circle with radius of 12. So the first thing we probably always need to do is draw a picture if we don't have one. So we've got a circle. It's got a radius of 12. It says find the length of the chord that cuts off the arc measuring 60 degrees. So if we make, remember the measure of the arc is also the same as the measure of the central angle. So let's just say we've got this central angle that equals 60 degrees. I know that this other side of the angle is also going to be 12 because my radii are always congruent, right? We need to find the length of the chord that cuts off the arc. So if the arc is here, the chord is what is made by connecting the endpoints of that arc. So that's the chord we need to find the length of. So let's take a look at this triangle. I can tell because two of its sides are congruent that it's isosceles. I also know one of the angle measures. I know in an isosceles triangle that the base angles are congruent. If the vertex angle is 60 degrees and the base angles have to be congruent, that's 120 extra degrees. If I cut that in half, these are also going to be 60 degrees, which means this triangle is equilateral, which means this chord is congruent to the other two sides of the triangle, which means that it also equals 12. Woohoo, look at all that symmetry. So that was your last set of notes. For now, these are the problems associated with 10.2 and 10.3. It's just 7 in total. Feel free to jump ahead and work on these. Otherwise, we'll work on them in class. And I love you and have a great weekend.